So then what's next? We're going to relate these two directly, and then we're going to try to come to some like combined equation that we can solve that tells us what the temperatures are going to be. Okay. So I've got the control volume now. Bring that along with us. So for this, what we're going to do is we're going to use that, that idea of local heat transfer. So let's see. Use local heat transfer. What do I mean by that? Well, let's write some things out here. dq dot is equal to TH, let's say it's at x, I'm just going to omit the x, but it's TH minus TC over RCV. So I guess, where did I get that? Okay, we're now making the separate observation that I know that like a differential amount of heat produces a change in, let's say, like TH or TC, right? So if I like scroll back up a little, that differential amount of heat is going to change it according to that ODE, right? I'm separately now observing the fact that if I just look at that little element, I can also relate the temperatures between the two fluid streams according to like a resistance formula, right? That's where that comes from. It's just a separate observation, but it's true, right? We know that that's the rate equation for like governing heat transfer locally. So then all we need to do is come up with like RCV, and then use this to combine it with the other equations. So RCV, this control volume resistance, is equal to our total. And we have to somehow scale it by dx, right? So it's dx is a portion of L. So if we just look at, say, multiplying it by the fraction that changes it to dx, we're looking at the ratio of dx to L. But we know that the control volume resistance is higher than the total, right? Because it's a small area. So we want the ratio to be L over dx. All right, so this scales my total resistance for the entire length down to a control volume resistance. Okay, once we do that, then we can write dq as dq dot equals th minus tc times, so now let's use the formula for conductance that we had before. So remember, conductance is 1 over R total. So this is going to be UA now times dx over L. Right? We see where it's just subbing in stuff we already have. All right, so now we can sub this into the energy balance. So we'll just say energy balance. And that gives us the following. So let's just copy it, TH, write that more clearly, sorry. TH minus TC over L times UA times dx is equal to C dot H times dt H x dx dx. Right, so we're just subbing in that dq that we just solved for. Now we've got to the point where you have that dx on the left and the dx on the right. And we always have to have those cancel, which is great because now they do. Right? Those cancel out. And so then we write for the hot side, which is what we're doing this for right now. So the result of this simplified, if we solve then for like dth dx, this is going to give us dth dx is equal to minus UA over C dot H times L times TH. This is actually THX, right? It's the current temperature at the current location minus TC, which is also TCX, right? These are local temperatures, solving for these. That gives us a hot equation. We do the same thing. We can do the cold equation. I'm not going to do it again, but just write it out. So this is dTC dx equals minus UA over C dot C times L times TH minus TC. Okay, so these are our governing ODEs. Two ODEs, 2 temperatures. Yeah, question. No, so these are, I should be more clear. These are the local temperatures. So I stopped writing it, but it's dThx, right, THX, TCX, same over here, TCX. Right, we're trying to come up with a model for these temperatures. We're trying to solve for the temperature as a function of position. All right, other questions on this? Okay. All right, so good. We have governing differential equations. Now the question is, how do we solve these, right? We have to figure out a way to solve both of these together. They're coupled. They refer to the same position x, so we solve them together. Okay, the way to do this is actually really, it's easy. It's trivially easy. You just subtract them from each other. So it looks like this. If we subtract the two ODEs, we'd say d dx, and I'm going to have the th, again, this is thx, minus tcx. So differential of both of those is equal to minus ua over L. Now I have thx minus tcx times the difference of the capacitance. So 1 over c dot c minus 1 over c dot h. I'm sorry, backwards. It's c dot h first and c dot c second. 1 over c dot h minus 1 over c dot c. Okay, so how does this help? Well, it sort of helps if we assume that this is actually something called theta. So let's say that it's a theta x. It's a substitution. We're just defining theta x to be this temperature difference. We just solve for theta x. So let's let that be true. Then we rewrite this. This is now d theta. Dx equals ua over L times theta. And I'm going to, let's see, bring that, how did that go? Th is Tc. I think I'm missing a minus sign here. And then we have 1 over c dot h minus 1 over c dot c. So actually now I have like an ODE in a single variable, which is great because I can solve it. This can be solved if we separate. So let's bring theta over to the left, and let's bring dx over to the right, and then integrate those two. So we do that. I will write that here. So this looks like the integral of d theta over theta equals minus ua over L times 1 over c dot h minus 1 over c dot c times the integral of dx. So one way to deal with this is you could just do the indefinite integral. You have constants of integration. You apply boundary conditions, that's fine. But actually a definite integral also works if you're careful about choosing the right locations. A definite integral is really just enforcing the boundary conditions as you go, right? It's the same thing. So let's do it with the definite integral, and you'll see that that will work. So here we're going to go, this integral on the left is from theta at x equals 0 up to theta at x equals L. And the integral on the right then has to go to the corresponding like x location. So that is just x equals 0 to x equals L. Okay, then we solve that ODE, and it looks like this. I'm going to save some, hopefully I have room. So that becomes the log of theta at x equals L over theta at x equals 0 is equal to minus ua over L times 1 over c dot h minus 1 over c dot c. The integral of dx from x equals 0 to L is just L. Okay, so the L's cancel out on the right-hand side. All right, so now all we have to do is go back and say, well, what did we originally say theta was? We have to, that's our temperatures. We just have to say, well, what's our theta at x equals 0, at x equals L? And now we have our final equation here. All right, so that looks like this. So we end up with a result of log theta x equals L is th out minus tc in. theta x equals 0 is th in minus tc out. And then that's equal to minus ua 1 over c dot h minus 1 over c dot c. Okay? Cool. So we have a nice relationship here. This is for a specific heat exchanger. This is for counterflow. Why is it for counterflow? Because that was what we assumed. If you look at the control volume in the upper right, that's a counterflow arrangement. If you did the same analysis for like a parallel flow, you're going to get a slightly different answer. And I guess it's only different in a couple ways. I could make you go to the book to, let me just write it so you have it. So parallel flow. It's going to be kind of scrunched on the corner here. So it's ln of th out minus tc out over th in minus tc in. That's equal to minus ua times 1 over c dot c plus 1 over c dot h. All right, so the important differences here are, I guess, these temperatures up here, and then the fact that you have a plus sign on the capacitance rates. But yeah, you just do the same analysis, go all the way through, and you get to that point. Questions on this? Okay. So let me just do one more thing here, and then we can be done for this point. Actually, you know what? That's all. So just to summarize what we're doing here, we've gone through a lot of trouble to come up with a relationship. So where would you use this relationship? Well, actually, if you look at it, what you're left with is something that relates just the inlet temperatures and the outlet temperatures, and this like 1 over total resistance, this UA. So if you have some piece of information like you know UA, you know the mass flow rates, say you know like 2 of the temperatures or something like that, you can use this to solve for one of the other temperatures. Right? It's an equation that helps you relate the two sides to each other.